Greetings and welcome once again to my new calculus channel. My name is John Gabriel. In the previous video, I talked about mathematics being the abstract science of measure and number, and I showed you that in the original Greek text of Euclid's Elements, the word for measures, measure, to measure appears hundreds of times, uh, almost everywhere in the book of the Elements. So I want to continue along that theme now and just show you a few things that I don't think most of you are aware of. So, first thing I want to tell you is that if you have two lengths, let's say such as the length of the circumference of a circle, let's say this green line, and the side of a right angle isosceles triangle, which equals to the diameter of the circle with this green line. Oh, by the way, these axes are not in a one-to-one ratio, so this may not look right, but I've done it this way on purpose because I want to have space to demonstrate the facts. So what you have here are two lines, okay? This line here is the circumference of a circle with diameter, let's say d, and this here is the hypotenuse of a right triangle, isosceles triangle, with equal sides d. So both of them are measured by d. And as you can see, the measurement here is just the unit. Okay, this, by the way, this happens to be the unit. If I turn numbers on, you'll see that that is the unit. X-axis, show numbers. Sorry, that's the y-axis. Don't want to do it on the y-axis. X-axis. Okay, so you see 1, 2, 3, etc. Okay, I don't want to show the numbers because they're not important. So in geometry, you can actually find many ratios that are in proportion to the given ratio here. And when you find uh, ratios, for example, for the circumference of the circle to its diameter and the hypotenuse to the side, you can find the quotient very easily if they have the same consequence. So this line here would be the consequence, but it can be any other line. So what I've done here is I've taken any parallel line to the green line and any parallel line to the blue line. If I arrange those lines, okay, so that the points coincide, I'm going to have the same ratio, okay? In other words, the same quotient. So the quotient of the orange line to the magenta line is approximately equal to this fraction here. And you can check it for yourself. It doesn't matter whether it's bigger or smaller. So if you decide to go smaller, the result will be the same, okay? And it can be anywhere along here. I'm just doing it along the ticks because it's easy to align. As you can see, if I try to do it on the, oops, do you see that? It's very hard to get it to show. Oh, I got it. All right, but you can, as long as those 2 points overlap, it doesn't matter where you put them. The measure of this ratio, this orange to magenta ratio, is always the same as the measure of the green to the blue ratio, the light blue ratio. Okay, so what I've done here is I've created a line here, this dark line here, that is equal to pi plus root 2. So in geometry, if you find that you can measure such a line with two line segments like that, then you can say that each of these line segments are a factor of this black line. Okay, and why can you do that? Well, look, you can do that because if you continuously subtract the green line until you can't subtract it anymore, and then what's left, this blue line, is divisible by the blue line, then it means that both of them measure the black line and they're both factors of of the black line. Okay, so many moons ago, I had a conversation with that idiot Marcus Cliver and Zealous Malem and a number of other stupids, Jean-Pierre Massager on Sci.math. They didn't understand these things. So I'm explaining these things to you again. And uh, really, if you arrange the ratios so that they are on the same consequent, or what became later known as the denominator, okay, the same consequent or denominator, then the antecedents, orange and magenta, or numerators as a ratio are the quotient, okay? And you can try this with actual numbers and you'll see that it works. And of course, if you want to do the multiplication, then what you would do is you would position the y part of this ratio along the x-axis and the x part along the y-axis. So you just flip one of them and you make sure that you take the ratio in the correct way. Okay, so if you want to say, for example, pi multiplied by root 2, then you'd need to say it's the same as pi divided by the reciprocal of root 2. So you'd flip this whole distance. Let me just draw it in. You'd flip this whole distance with this whole distance. In other words, you'd put this black line along the y and this one along the x, okay? So that's how you would do it if you were to do a multiplication of pi by root 2. Or you could also do it the other way. You could, for example, put this first and then move this along and then just take the reciprocal of pi and then again the quotient, because multiplication, as I said in the last video, is just a reciprocal measure. Okay, it is division, but it's a reciprocal measure, and I showed you how to do it. And of course, if you go to my world acclaimed article, Theory of Fractions, from Book 5 of Elements, it explains these things in very fine detail. And if you want to understand number, this is the only way you can do it. Nowhere else is this information published. Nowhere. And you're getting it for free, okay? All this is free information. I've written it both in English and Greek as a tribute to my late mother, who was a Greek. And then, of course, I'll also give you a link to one of my free books, The Ultimate Book of Numbers. So let's summarize once again. In geometry, a common denominator is not the same as in algebra. So, for example, you can't talk about the least common denominator, because with line segments, you can use any line segment and or parts of it to measure another line segment. 2, geometry allows smaller or larger magnitudes to measure each other. And of course, in geometry, a magnitude p is a factor of a magnitude q if p measures q as a whole. Another way of saying p is a factor of q is if what remains after p, let's say this is p, has been repeatedly subtracted from q. Let's say this whole thing here, not from q, by the way, has been repeatedly subtracted from the black line. So this is actually wrong. It's subtracted from the black line. Say r, and let's say r is the remainder. Then if r is measured by q, then of course the line segments are both factors of this line segment. So I messed that up a little bit. So what I should have said there is that, let's see if I can correct it now. I said another way of saying P is a factor of PQ. Okay, so is a factor of the magnitude PQ if P measures PQ as a whole. Another way of saying P is a factor of PQ is if what remains after P has been repeatedly subtracted from PQ, say R, where R is measured by Q. Okay, so now that is correct. Okay, so right, sorry about that, but got vision problems and I'm getting old. So there you have it, and that's pretty much it. I'll place links in the details section. and also a link to this applet, which I'll upload, and you can play around with it and you can change these values to, things that are easy to find the quotients, like 4 divided by 2 or 16 divided by 8 or whatever, or 9 divided by 3, etc. And you can see that these values here will be the quotient, okay, or the multiplication if you switch the parts around. So this is how you can find a common consequent anywhere by drawing parallel lines to the ratio and positioning those on the same point. Then you have another ratio which is in proportion. It's not equal to, but it's in proportion, which means its measure is the same. Okay, so ratios that are in proportion have the same measure. They're not equal, but they have the same measure. If you're not already a subscriber, become one. Click like and follow me on Academia. I'm John Gabriel, and this is a new calculus channel. Till next time, goodbye.